Hello, everyone. So in this talk, I will present our work on high-throughput secure three-party computation with anonymous majority, breaking the billion gate per second barrier. This is a joint work of the NEC team and Bar-Ilan University. Okay, so in secure multi-party computation, or MPC, we have a set of parties who wish to compute jointly some functionality on their private inputs without revealing anything about the output of the computation. Now, there are many applications for this. Basically, whenever you have a problem that involves distributed computation over some sensitive data, MPC could be the answer. When designing secure protocols, there are two main threat models. The first is the weak semi-honest model, where we assume that the parties follow the protocol, but may want to learn more than they are allowed to. And the stronger, more realistic, malicious model, where the parties can basically do whatever they want, and we cannot assume anything about their behavior. Now, the current situation, the current status of the MPC field is that there are already some real-world problems that we can solve using MPC. There are several companies which have products that are based on MPC, but in many other cases, MPC is not considered fast or efficient enough to solve real-world problems, and this is especially true for when we deal with malicious adversaries. In this work, we show that large-scale secure three-party computation is practical, even when we require security in the presence of malicious adversary. And we provide some general techniques for improving efficiency of protocols that are based on the cut and choose method that I will present in a few minutes. So in our setting, we have three parties who wish to compute jointly some functionality. We assume an honest majority exists, which means that exactly one of the parties can be corrupted, maliciously corrupted. We assume that the functionality is represented by a Boolean circuit, and we consider security with a both, which means that the security requirement is that if the corrupted party cheats, then the honest parties will detect it and abort the computation. Okay, now when we measure the performance of protocols, there are two main ways to do that. So the first way is to measure how much time it takes to compute a single function. This is what we call the latency of a protocol. On the other hand, we could measure how many functions we can compute in, let's say, 1 second. This is what we call the throughput. Now, these are not just two ways to measure performance, but actually two different goals that are translated into different approaches of how to design a protocol. Specifically, if we want to achieve low latency, then usually we would like to minimize the number of rounds of communication. This will be usually done using the garbled circuit approach, where you have several rounds of communication, but in each round you send a large amount of data. The parties send an encrypted version of the circuit, so this is big messages. On the other hand, if you want to achieve high throughput, then you will usually care less about low bandwidth and simple computations, and you will care less about the number of rounds of communication and more about low bandwidth and simple computations. The reason for that is because even if a party waits for messages to arrive, then meanwhile it can start the next computation. So in this case, we will focus on pipelining the computations in order to achieve high throughput. And this will be done using the secret sharing approach. In our case, this is our goal, to achieve high throughput. And we will follow this approach, the secret sharing approach. So the starting point of our work is the malicious protocol from a previous work of ours. It works in the following way. There is an online protocol where the parties share their inputs using some secret sharing scheme, and then they run a cheap semi-honest protocol to compute the circuit. And then before we reconstruct the values on the output wires, we have a verification step, because in the semi-honest protocol, obviously, the corrupted party might have cheated. So we need a verification step where we verify all ends gate computation. Why only AND gates? Because in other gates, the computation is locally. You don't need to have any interaction, and therefore the corrupted party cannot cheat. So only in AND gates we have interaction, and therefore we need to verify that the computation was correct. This is done using random multiplication triples that we generate in a preprocessing protocol, in an offline protocol. And if we use the parameters that I will soon present, we have that the online protocol is pretty cheap. It requires communication of 3 bits per AND gate for each party. And the offline protocol is the bottleneck, which requires each party to send 7 bits per AND gate. We measure it by how many bits per AND gate, because this is what determines eventually the throughput of the protocol. So in this work, we focus on making the preprocessing protocol less of a bottleneck. This will be our focus here. So how do we generate these multiplication triples? So first, what is a multiplication triple or a random multiplication triple? So this is a triple of shares, A, B, and C, that are shared among the parties, such that A and B are sharing of random values that are not known to any of the parties, and C equals A times B. Now in our protocol, we can generate the random sharings without any interaction, and then we generate the sharing of C of A times B using a semi-honest protocol, semi-honest multiplication protocol. This process requires only 1 bit of communication, so this is a very cheap process, but of course, the corrupted party might have cheated, and the multiplication triples that we generate may not be correct. So how do we verify that the triples that we generate are correct? So this is done using the cut and choose method. How does it work? So we start by generating many triples, let's say M triples, in a semi-honest way. So these triples might be incorrect. And then we randomly permute these triples. The array of triples, we randomly permute it. And the key here is that the permutation cannot be known to any of the parties before they finish generating all the triples in the previous step. This is key. This is key for the security of the protocol to hold. So after we permuted randomly the triples, then we open the first 3 triples in the array. By opening, I mean that the actual values are revealed to the parties. And then, if one of the open triples is incorrect, then the honest parties will detect it and abort the computation. So this is the first test that we have to ensure that the triples are correct. Then if we passed this test, we take the remaining triples and split them into n buckets of equal size. In each bucket, we have beta triples. Okay, and then we have this sub-protocol in our protocol that allows us to verify the correctness of one triple using another. So we run this sub-protocol many times, each time to verify the first triple in each bucket using the other beta -1 triples. And the property that we have here is that if one of the buckets is mixed meaning that it contains both correct and incorrect triples, then the honest parties will detect it with probability 1 and abort. So the only way that the corrupted party may win by generating a bad triple, by output a bad triple from the preprocessing protocol, is by having only fully bad buckets. But this, is, of course, happens with small probability because there is a random permutation, and the adversary does not know the random permutation in advance. So if we passed all these tests, then we take the first triple in each bucket and output it from the preprocessing. And this is the n random triples that we use later in the online protocol to verify all n gates computations. So if we look at the communication cost of this process, we obtain this formula, okay, which, not surprisingly, depend on n, the number of triples that we output. Beta is the size of the bucket, and C is the number of triples that we open. Obviously, if we want to minimize the cost of the protocol, we would like to reduce the parameters beta and C. On the other hand, the cheating probability of the success cheating probability of the adversary also depends on these values, on these parameters. So what we have here is some trade-off. If we want lower cheating probability, then we would like to increase beta and C. If we would like better efficiency, then we would like to reduce beta and C. Anyway, in our protocol, in the starting point protocol to achieve 10 bits per AND gate, as I presented in a few slides earlier. Then we set beta and C to be equal to 3, meaning that the size of each bucket is 3 triples, and we open overall only 3 triples. Okay, so and with this we achieve communication of 10 bits per AND gate. So we started by implementing this baseline protocol, and this yields a throughput of 500 million AND gates per second. What we will see soon that we can double this throughput and break the 1 billion AND gates per second barrier. So the first thing we did is to benchmark the results. Okay, I don't know if you can see there in the circle. So the first major bottleneck that we found is the shuffling of the data. We shuffle a very large array, the random permutation, and this comes with a cost. And the reason why it is so expensive is because we have cache misses. We use the Fisher-Yates algorithm, so every time we swap two cells in the array, and this brings cache misses. So our first optimization is an optimization of constructing a cache-efficient shuffling. Without going into all the details, the idea here is that we take an array, we break it into subarrays, then we random shuffle each subarray separately, and then we shuffle the subarrays in the large array, where the last step is done. In the last step, we don't shuffle physically. We don't move the subarray physically in the memory. We use index table and shuffle the indices. So the shuffling of the subarrays, in the shuffling of the subarrays, we actually move physically we move the data from one place to another. But for the shuffling of the arrays in the big array, we use index table. So eventually, we only shuffle each time small arrays, and then it fits into the cache, and then there's no cache misses. The point here is that this is not a random permutation. So we had at the beginning random permutation, now we don't have. Even so, we managed to prove that with changing only slightly the parameters, we still achieve the same level of security. Specifically, as you can see, we have the same communication. We need the same bucket size, but we need to open a little bit more triples, 1,000 triples. But this is not very significant. We generate 1,000,000 triples, so to open 1,000 triples, it's not significant. And with this optimization, we managed to increase the throughput by 25%. So we are getting close to our goal of achieving 1 billion AND gates per second. Our second optimization, which I won't go into the details, is reducing the size of the bucket and therefore reducing the communication of the protocol. So the intuition here is that we can, each time we compute an AND gate, we actually generate also a multiplication triple. So we can treat it as if it was one of the triples in the bucket. Of course, it is not a random multiplication triple, so it is not that straightforward. But we have this process that we call on-demand verification, where we choose at random the triple that is used to verify in the online. And by this, we kind of match each AND gate triple to a bucket from the offline. This increases the computational work in the online a little bit, but it allows us to reduce the size of the bucket from 3 to 2, and therefore reduce the communication from 10 bits per AND gate to 7 bits per AND gate. And this brings us to almost our goal. We are getting close. At this point, we went back to the benchmarking of our protocol. Now things have changed. Bottlenecks that we have seen before are not bottlenecks anymore. But now there is a new bottleneck. I don't know if you consider the word SHA-256. It appears everywhere. And this was not a bottleneck before, but in our protocol there is some step as part of the verification where the parties compare their views. This is done by they accumulate the views that they've seen during the computation, and then they hash it, and then they compare the hash values. So now this has become a bottleneck. So what we did here is to replace the SHA-256 with GMAC. Why is it sufficient? I encourage you to read in the paper, but this allows us to use for GMAC. We can implement it very efficiently with AES-NI, and this reduces the cost significantly. And using this optimization, we manage to achieve our goal, and this brings us to 1.1 n-gates per second. And we managed to break the 1 billion n-gates per second. Yeah, so to sum up, we demonstrated that it is possible to achieve fast rates, even for malicious adversaries, in a very specific setting, the three-party settings, but it is much more than in any previous work. So we achieve rates, so I didn't say at the beginning, but we also implemented the semi-honest protocol by itself, and this achieves a throughput of 7 billion n-gates per second. So the malicious protocol is only 7 times slower than the semi-honest protocol, 1 billion n-gates per second, which can be translated to assuming that, let's say that we want to compute an AES function. So this translates into more than 200,000 AES operations per second. And we believe that this work can significantly extend the application for MPC. Thank you very much.
So we have time for questions.
Hi, Sahar Mazloum from George Mason University. That was a very nice talk. I really enjoyed it. My question is regard to the shuffling process that you're doing. So in the shuffling, all the parties are involved, or just the shuffling? Who is doing the shuffling, basically, in this process?
How did they do the shuffling?
Yes.
So,
Who is responsible
I didn't mention
that?
it. So what we do here is that the parties communicate to generate a seed, and then they use a pseudo-random generator to generate using the seed as much as randomness as they need. So eventually they need only to this is constant communication for generating the seed. This is done by they generate random sharings and open it, and then they have a seed, and then they can use it to generate as much as randomness as they can. So in terms of communication, this does not cost much, but as we have seen, it comes with a computational cost that we managed to reduce.
Do you need it to be like generate all the possible permutations, or just?
No, it's just one permutation that the parties don't know in advance, and that's enough.
Thanks.
So I have a question regarding detecting who actually deviated from the protocol. So can you reliably say, do you have enough evidence to blame one of the parties?
No.
And specifically with the multiplicative MAC, it seems that it's really difficult to do that, or are there more fundamental issues?
Yeah, well, we don't know when the parties are both, they don't know who cheated. No, we don't know. There are protocols that can achieve that, but not in this protocol. No.
And is it something that will be much more expensive, or is it?
It would be difficult. It will reduce the efficiency of the protocol. It won't be easy, especially in the secret sharing approach. It's not that easy to do that.
Okay. Any other questions? Or? So maybe one last one. So what can you do with 1 billion gates beyond AES? What's a typical non-cryptographic applications with 1 billion gates? What are your favorite one these days?
Oh, that's the $1 million question. I have nothing in mind, but we thought about a few things. I don't have something specifically in my mind now.
Okay, well, thanks.